Hello, welcome. Unfortunately, it's me. I couldn't get Bruce Schneier to come in and teach this lesson, but this week we'll be talking about cryptography. It's chapter 9 in our ethical hacking class, the second book in the second class, and a lot of hard S's in that sentence. We get done with this, and hopefully you can tell us all about public key crypto, the whole digital signature thing, the RSA, various algorithms in security. Tell me what a message digest is, and understand SHA, as well as understand the secure socket layer and SSH, or the secure shell, various methodologies for breaking codes, cryptographic attacks, and a handful of the cracking tools that are out there to crack cryptography. Not too tall of an order, right? So cryptography, the practice of hiding stuff from other people. That's good. Symmetrical key cryptography is super powerful. It is theoretically possible to create uncrackable symmetrical key cryptography. However, the trick is that key that you have would need to be pretty huge, and it'd have to be completely secret. So on the internet, where nobody knows you're a dog, but also where individuals who haven't met each other want to be able to communicate securely, have a problem when they go to talk to each other. A symmetric key system with a super duper long key is completely secret, but if you can intercept that key while I'm giving it to somebody, now we've got a problem. So public key crypto to the rescue. It is an asymmetrical key system. So that means there's some sort of function that allows me to have a public key that I can put out there for anybody, and a private key which only I have. And that can provide us with the following things: confidentiality, so it's secret because we encrypted it; integrity, we know that the file I sent is the file I sent because magic. No, because you can use either hashing function or something to prove that it is what we were sending. We can authenticate, meaning you'll know it was from me because the public key is tied to the private key, which theoretically only I have. And non-repudiation, because I can sign a key using my private key that my public key can decrypt to prove what went on. So if you have a copy of my public key, only I, the owner of the private key, can decrypt it. So here's an example of how that might work. Not necessarily a wonderful example, but an example. Notice the public-private key icons here. I'm kind of a fan. But Peter signs a document here with his public key, goes out over the internet, comes in. He signed it with his private key. I think I said public. Comes back in. Using his public key, they decrypt it, and now we know that it's Peter's message. Pretty simple. It's asymmetric, which is cool. So a digital signature is when you cryptographically authenticate something. A hash function, which you may remember from talking about passwords, is one of the ways you can create and verify a digital signature. And there's some sort of, you use a hash to create a digital fingerprint of a message or whatever it is we're trying to sign here. Then we take that hash and we sign it and we encrypt it. So thus signing it. And now if you use my public key to decrypt the hash, you see the hash that matches up with the message, you know that only I could do that. Voila, we've proved that Rosamund actually created that signature, pardon me. So public key cryptography, that's just how we use some trusted source to verify that Rosamund's key pair belongs to Rosamund. Handy, right? But now you need trust. So you've got to have some sort of certifying authority, like, hey, why not Microsoft IaaS? Something better than the Chinese post office or the myriad other somewhat sketchy people you trust. If you look at your browser or operating system, there are some pretty sketchy characters in there. Anyway, these certificate authorities, they sign the public key certificate with their private key to assure you, the end user, that public key does in fact belong to who they say it belongs to. So here's the very simple flowchart of how that all works, right? All based off, here's my private key. We use some public key encryption, create a signature that goes over here and off to the internet too. You can also use this for a document. Take a signed document, plus a signature, sign it, do the whole public key algorithm. When you receive it, take my public key, decrypt it, you get the original hash, you know that it was encrypted with my private key. You take my document, you take the hash, you compare it with the new hash that you create on the output, and based on that you say, maybe that's his document, maybe not. You accept it or not. RSA, the name of 3 dudes, Rivest, Shamar, and Adelman, uses a modular arithmetic, clock arithmetic you might remember from elementary maths. It's the remainder, to put not too fine a point on it. And it uses computations using like ridiculously big prime numbers that we're not going to expect you to be able to figure out in your head. Here are the encryption functions, which you will not be expected to memorize. But the upshot is if you use a couple of great big prime numbers, and by great big, I mean great big, come up with a modulus, you create this trapdoor function, and out pops decryption. And I'll put a link in underneath of this lecture that tries to demonstrate the maths here with colors. Easier to kind of wrap your head around public key cryptography using paint as opposed to numbers sometimes. And for the purposes of this course, it's just important that you understand that this is a thing, that public-private key cryptography exists and that there are functions that make it happen. You will be expected to regurgitate sort of trivia about encryption algorithms for the ethical hacking cert and for other certs out there on the internet. So things to remember: RC4, 5, and 6. Remember that it is a variable key size based on random permutation. RSA5, Rivest made it for the RSA data security, at RSA data security. RC6 is similar, uses integer multiplication, and the use of 4-bit working registers rather than 2-bit, so it's bigger. Blowfish and other ones. Secret key cryptography, meaning symmetrical, that the key goes from 32 to 448 bits, the kind of thing that makes a great test question, wouldn't you think? So these sorts of numbers vary based on a lot of things, like including processing speed, but 1,019 years to break on a 128-bit message based on CPU speed at the time and so on. So if you up the size of the keys you're using in encryption, doubling the key space, it gets a lot bigger. Most of the more advanced, if you take 128 and go all the way to 1024 or 248, they get really big, and decryption times reach into the like longer than we expect the universe to last. Using modern processing power, the stars would burn out before you manage to decrypt it. So hash functions, maybe we should have covered this first, but you take a file of any length and you come up with a single fixed length number to represent it between 128, 256 bits in length. It's one way because based on that number, the 128 to 256 bits in length number, you can't go back and create the file. So they are resistant to attack. Generally, they tend to be unique, although they're sometimes subject to what's called the birthday attack, and widely distributed. If you've paid attention to the news recently, researchers at Google managed to create what's called a collision, where they had 2 separate PDFs, and they produced the same hash because of some jiggery pokery with the contents of those PDFs. So that means that if you were using that as a digital signature A would look for all the world like digital signature B. So we needed to move on and use a little better crypto. And that's the kind of thing that goes on all the time with cryptography. It's an arms and armor thing. The key to it is making sure whatever you're protecting currently, the amount of work it would take to get into it exceeds its value. You know, so if you've got a $1 secret, as long as it takes $2 to get into it, you're fine. If you've got $1 million secret, you want it to take a couple of $1 million to get into it, and so on. So hashing functions, they let us have integrity for document management. And why is that important for hacking? Well, say you downloaded something off the internet. You can use one of these fancy schmancy message digest functions to come up with a unique number for that download. If somebody had a different executable file, say it's a Microsoft Word installer. If evil hacker man stole that installer, added their Trojan to it, and put it back online, the message digest for that executable would be different. And if Microsoft published the message digest for the known good file, when you compared the message digest of the file you downloaded, you would say, aha, this is not the file that I wanted. Could be a trap. So great for document management and for signing things, but also great for making sure the application you downloaded is what you think you're getting. So here's a graphic of that message digest function. Take document 1, spits out this fingerprint, document 2 spits out this fingerprint, and reduces it down to a hash. So it takes whatever size this file and this file are and reduces them down to 128-bit signature, fingerprint, hash. MD24N5, the message digest family of algorithms. Input can be whatever you want. You always wind up with 128 bits on the way out. These were widely used, but are beginning to be depreciated as time ticks on. Their security is becoming something of a concern. SHA-1, the secure hashing algorithm, built into the secure hashing standard, was developed by our friends at the National Institute of Science and Technology. It is like MD4, accepts a message of X bits in length and produces an output of 160. The US government's been working on a set of publicly available cryptography standards. What could possibly go wrong? SSL, sometimes called TLS, is using, called TLS these days. SSL is sort of depreciated now. It's supposed to provide secure authentication between two people, applications such as a client and server. The whole secure internet thing depends on using asymmetric encryption to find somebody's public key, their signature of who they allege to be, and then create a handshake. We exchange private keys after we've connected to each other using public keys. Again, there's a great video I'd like to share with you about that. That does all that. Back in the day, you could open up Multizilla to tell you about where something was from. You can still get into the signatures of your websites that you're looking at and see the certificate that they are signed by. It's when you get that little green lock up in the corner. So the handshake is hello from the client to server. Server responds with hello. Connection gets established, then it sends on over a certificate. Server sends a hello that says, hey, we're done shaking hands, you got my certificate. Client gets a certificate request, transmits the changed cipher spec message. Hey, what type of ciphers can you use? There's a bunch of them out there, and we run into problems when this process says, hey, I support a really old and crappy cipher with known vulnerabilities. That gets us in trouble. SSH, SSH2 lets you securely log into a computer and do all sorts of other falderall after you've connected to another computer, such as set up tunnels. Very reliable, very secure. You've heard me harp on, use SSH instead of Telnet in any application where you can. SSH can use a password, can use key cryptography, can use Kerberos, can use hosts if you want. A good idea to use some combination, right? The upshot is, in an SSH tunnel, all of the stuff going on here is encrypted, which is good, which means anybody who is not privy to the encryption mechanism can't listen in. That's what you want. So since that connection is authenticated, there's no spoofing. Can't mess around with source routing. Can't mess around with DNS spoofing because the server you direct me to won't have the key that I'm expecting. In fact, the first time you connect to a key, say using PuTTY, you'll get this warning that says, hey, the signature here isn't in my list of known good signatures. Is that cool? And you have to say yes. And if you see that message later on, then you got something to worry about. Don't have to worry about people in the middle sniffing things up. Don't have to worry about folks in the middle exploiting stuff. If you've got X11 running over SSH, so if you're using your windowing system over SSH, can't nobody see your stuff, which is good. Disk encryption is similar to encrypting a text message, except you want all of the stuff on your disk encrypted, which is not bad. Depending on your adversary, you might look into different softwares out there. Microsoft's BitLocker, I know, don't kill the messenger, is generally enough if your adversary is the guy who stole your laptop because you left it on a taxi. Maybe not good enough to withstand the NSA, since conceivably Microsoft could get into it for them. But pretty good. If you needed to send something through the mail, wouldn't be a bad idea. But it means your system is secure. Most phones operating systems support that now. The idea being phones are very easy to misplace or have somebody pinch them from you. So encryption, your friend. RSA factoring challenge. So breaking encryption is always fun. RSA Labs ended this thing in 2007, but they would try and go through and figure out like the best way to factor large numbers, since that's how a lot of cryptography does its thing, through the use of that. But factoring this is, again, processors get faster. This sort of thing gets quicker and quicker, but using 215,000 Pentium, ooh, the very zippy Pentium. Man, it's got to be relatively recent Pentiums, just 4 gigs of RAM was around. Just notice that as the length of the bits increase, the number of machines to crack something increases, and the amount of memory it takes to calculate all this stuff increases. So it's a big deal. Distributed.net hosts points and prizes for helping solve encryption challenges through distributed computing. They were sponsored by RSA Labs to get this whole thing off the ground. So what can people do to break through your crypto? Well, we can try to exhaustively search every single key out there in reality. Depending on how big the key is, this starts to down here and creeps up and then goes way up. This is a long time. 10 to the 18th power years is a whole lot of time to get something like that accomplished. So you'll see that the bigger they get, the faster they go. A little one isn't so bad, but a giant one is going to give you problems. If you dive deeper into cryptography than we will in this course, there are a bunch of different types of attacks that you can use to try and break encryption. The easy ones, these require a lot of work. If you only got the ciphertext, if you know the plain text, if you can choose the plain text, so you have access to the encryption cipher tool that they use to do the encryption. If we can change the chosen plain text, it's good. If We can choose what the ciphertext looks or choose the key we use. Those all give us different hooks into trying to crack the cryptography in question. These ones are a little easier to grasp for your average penetration tester. If I can get the person who knows the password in a room with a chair that I can strap them to and use a rubber hose to extract the file from them, easier than any of these. And if I can just pay somebody off, again, way easier than any of those. So remember that cryptography is only as good as its weakest link. I believe there's an XKCD that explains the rubber hose attack pretty well out there too, but I'll leave hunting that down as an exercise to the viewer. Specific to RSA, there are some esoteric attacks out there. You can brute force it, and you can use the same kind of chosen ciphertext. If you start off with small encryption exponents, makes it easier to figure out. You can attack the error analysis. You can check the modulus. There are tools out there like ORFcrack, John the Ripper can enable WebCrack. Your idle CPU time can be thrown at these sorts of processes. Clever Safe Grid Builder, PGP's out there, Command Line Scripter, CryptoHaven. Microsoft's got a whole suite of cryptography tools like these. So you can create certificates, manage certs, etc., etc., etc. Go through and out there. I think also TrueCrypt or VeriCrypt probably bears mentioning. You might want to go look that up and understand it. It's varying forms of disk encryption. I think that's a good high-level overview of this stuff. So public key crypto lets us send confidential messages even though we've never met, as long as you trust whoever is saying that that is in fact my public key. RSA is one of the de facto crypto standards out there. An MD5 sum or algorithm is a digital signature type of deal. SHA has sort of supplanted that in a lot of spaces, although small inputs and small key size is kind of a problem for them. It's not broken. Just need to move on to the newer versions. SSL, now TLS, lets us stay secure on the internet by encrypting our stuff. RSA, RC5, a fast cipher designed by RSA. And that's all we think you need to know about crypto for this particular course and test, although it is definitely fascinating and worth a deep dive, especially if you're a little bit mathy. Bruce Schneider's Applied Cryptography might be the definitive work on the subject. You might want to check it out. That's it. See you guys later.